All right, here we go. So there's things that we can't always have as a go-to. So the measure of AB is equal to the measure of CD. It's not a go-to right now, even though it looks like a rectangle. Now, some of you said, well, I got my compass out and it matched up. Good if you did that. If you measured with something with numbers on it, I'm going to say no, you can't go with that. The measure of angle A is a right angle. You don't have the knowledge of how to construct that yet. It looks like it's right angle, but again, we can't assume that. Yeah.
But what if you measure it with your protractor?
Ooh. I'm going to say yes and no on that one.
Okay.
The reason I'm going to say yes and no, so both answers would work. I think that's an adequate thing to do, but right now, like, you couldn't assume that that's a right angle just because it looks like a rectangle.
Okay.
So I think both answers are fair assessments. Measure of angle A is equal to measuring angle B. Again, they do all look like they're 90-degree angles, but we don't have enough knowledge to say that they're the same. Okay? B is between A and C. Well, if you were to take the path to it, I guess you could say that, but I think we're having to say you have a straight line, you have a point in the middle of it or somewhere on it. So I don't think you could say B is in between A and C right now. A, B, and C are non-collinear. I agree. Yes. Any questions on the first part? Number 2, line L is a straight line. We could say that because we need to assume all lines are straight. We're not drawing anything with a curve. Segment EB forms a right angle with line AC. EB forms a right. We don't have enough information to justify that. We don't know if B is exactly in the center of AC, so we can't even do the perpendicular bisector to prove it, so we can't say that. ABC are collinear. That is true. D is a point in the interior of EBC. EBC, D is a point. I'd go with that. Point D is in there. Measure of CBD is equal to EBD. We cannot say that. We don't know if EB is the angle bisector. The measure of CBD and the measure of CBE is less than, again, we don't know that for sure. Again, we can't assume that we say it's correct. And I wouldn't go off the measuring of it. The diagram can help determine which conclusions are allowed to be made. ABC are collinear. ABC, nope. C and E are collinear. Yes. Okay, 2 points are always collinear. Yes, ma'am?
I have a question on 2.
2, which letter?
F. So I said yes because it's like in between, so it's like.
Oh, you know what?
On the answer.
You're right. You're right. I misread it. Being that CBD is inside of the whole angle, yes, you could say that. I'm sorry. I thought it was meaning I can't read. You are absolutely right. So F is yes, because that angle is inside the bigger angle. I was looking at it as 2 angles equal. Yeah.
I don't get how 2D is.
2D. D is a point on the interior of EBC. So we have this angle EBC. You know, it's this angle right here. This is a point that's inside of it. That's all it's doing.
It's just anywhere.
Let's see. 3C. D is between A and E. I'd say so. It doesn't say it's equal. It says it's between it, right? The measure of AD is equal to the measure of DE. AD, DE. Lines of AD. We don't have enough information to justify that. They are both line segments. We don't know if the 2 line segments are different. I'm loosening my tie. I'm sorry. All right. The measure of ADF is equal to CDE. That's true. Anyone know why it's true? Yeah. They're not adjacent. Adjacent is right next to. Yeah.
There's like reflections of each other.
They are reflections. Is there a term that anyone knows yet? Go ahead. They're called vertical angles. Good. Okay. Any 2 points there exist exactly one line. True. That's number 4. Number 5. Through any 3 collinear points, there is exactly one line. 3 collinear points, there is exactly one line. Yes, that's true. Through any 3 non-collinear points, there exists exactly one plane. That's also true. In space, if 2 lines don't intersect, they must be parallel. That's false. Again, we're talking about in space. So if you talked line going from that wall to that wall on the floor, and we talked a line going from that wall to that wall on the ceiling, they will not intersect. They're in different planes. They are not parallel, though. In a plane, 2 lines that don't intersect, they must be parallel. Is that what we just said? Oh, in a plane. If 2 lines intersect, then they must be parallel. That's true on a plane. If on the same thing, if they don't intersect, parallel works. Through any 2 points, there are infinitely many planes. That is exactly correct. You have these 2 points. You have a 3-dimensional fan of planes that go through those 2 points. That's why you need the 3rd non-collinear to stop the thing. Is this number 10? In space, any 3 non-collinear points will form a triangle in space. Sure? I'll say that now. If a line and a plane intersect, their intersection is a line. Gosh, that's got to be a sometimes. Is that a choice?
No.
So if I had a line right now, if I was thinking about it, if I were to take a line and do this and touch my board, it's going to intersect at a point. The only way I'd say it was a line is if that line was lying on that plane somehow. But right now, we'll say no. The intersection of 2 planes is a line. Yep. Ceiling and the wall make a line where they intersect. If A is perpendicular to line B, which is in plane M, then line A is perpendicular to plane M. If line A is perpendicular to line B, and I'm reading that B is in plane M. Is that how you're reading that? Then line A is perpendicular to plane M? No. Okay, so this is my plane up here, and I have my line. Okay. This, like this, would make it perpendicular to this line. But this is still perpendicular to the line as I do this. It is no longer perpendicular to the plane as I tilt it, but it's perpendicular to the line. That's how you'd have to think of that one. What number am I on? 14, thank you. Through a point on a line, there's exactly one perpendicular to the original line. Through a point, I'd say no, because they didn't say it had to stay on a plane. You could have that perpendicular line making a 360 circle around it. 16. If a line is perpendicular to B, if A is perpendicular to B and line B is perpendicular to line C, then line A is perpendicular to line C. I'm going to say yes, that falls into the transitive property, which we'll get to. Is that what they say? Yeah. This is false. If line A is perpendicular to line B, line A is perpendicular to line B, and B to C, A to B. Oh, I guess not, because we could have this. We could have that, look like that. Something like, I don't know, something like that to where they're not perpendicular. So you have 3 planes. Okay, these don't run on smartboard. This does. Point A is on plane P. Through point A, there's exactly one perpendicular line. perpendicular to plane P. Yes. Cool. That is good to go. Feeling all right? Make sure your names are on those staplers far side. First and last names, please. Grab the wrong one.
I was like, what the heck is this? I don't remember doing this.
Okay. Today, develop an understanding, then apply the segment addition and subtraction postulates. That just means we're going to add stuff together to get longer or take them away to get shorter. Develop an understanding what a midpoint is, and then apply understanding to solve problems. So midpoint means the center. Just cut something in half, right? Does that seem okay so far? Let's do it. Woo! Oh, and geometry rule is accepted without proof and cannot be proven to be wrong. A geometry rule that is accepted without proof. Oh, I think I can move this out of the way. It's a postulate. Okay, so a postulate is a rule that we don't have to prove. So what I want you to start thinking about is there are certain laws that are out there. One of them is called a postulate. A postulate is proven. It doesn't have to be reproven. We could use it to justify other things happening. A geometry rule that can be proven to be true is called a theorem. So you have theorems and postulates. Okay? So you can prove theorems using postulates. A postulate is a geometry rule that is accepted without proof and can't be proven to be wrong. And then a theorem is a geometry rule that can be proven to be true. Okay? So sometimes things are rules, sometimes things are postulates. Those are good things that we want to keep going. You're going to use rules and postulates to justify why something takes place and why something doesn't. So pay attention to your rules and postulates, and we'll make sure we highlight upon them. Cool? All right, we're going to hide them for next period. Yeah.
What would be like an example of like a postulate and a theorem?
You ever hear to like side angle side or side side side? Or angle side angle? Pythagorean theorem. The sum of the squares of a right triangle equal the square of the longest side.
Plus b squared equals c squared.
Yeah. And then postulate, can't think of one offhand that you would know right now, but they'll come up. Okay, note, BE refers to the line segment itself. BE refers to the length of the segment. So we could say that BE is equal to 10. So note, segment BE refers to the line segment itself. So then we could say BE refers to the length of the segment. Notice how we have BE written below. We don't say have the segment line above it. Make sense? We've already, yeah.
Why would we not have it above it?
Because it's referring to a length. It was referring to a length, and then of course it's kind of redundant. Are you necessarily incorrect if you have a line segment line above it? No. But just be aware that if I give it a numeric value, I don't need to have the line segment line above it. Can I move on? All right. Segment addition postulate. Ooh, it's a postulate. Here's your thing. If points A, B, and C are collinear, so they lie on the same line, and B is between A and C, then segment AB, so from here to here, plus here to here, will equal the whole distance. Is there anything I have to remove up there? I don't know why they have moved.
There should be a space between, in the second line, there should be A, B, and B, C. There should be a space in between the two B's.
So if A, B, and C are on the same line, B happens to be between the two, the segment of A and B added to B and C would result in the longer segment being AC. So that's called your segment addition postulate. If I add one segment to another segment, I get the longer segment. Make sense? Okay, move on. Go back to God. Like that. You good? All right. In a similar manner, we can reverse this concept and create the segment subtraction postulate. Okay, so we can reverse our thing and create the segment subtraction postulate. If two segments have equal length, if two segments have an equal length and smaller segments of equal length can be taken away from each, then the remaining segments must be equal. So if I have something that is the length of my fingers, and I have something else that's the length of my fingers, and I have something that's shorter than the length of my fingers, and I want to take away from each one of them, then the new segments on each one would be equal. It's like in algebra, if you were to have x plus 7 equals 10, if you subtract 7 from both sides, you're still created to be equal. So that's where your postulate comes from. Let's see, is there anything more down there? Oh, yeah. Can I move this back over top? Segment. All right. That way next period has stuff. What logical conclusion could be made? We could say that AB, so if we knew that AC is equal to BD, if I were to subtract this little amount, so if I wanted to remove this, being I'm taking that from AC and I'm taking it from BD, and they told us that AC and BD are equal, what logical conclusion could be made? The segment from A to B is equal to C to D. This is the example of the segment subtraction postulate. So you're taking away you already are told this. This equals this. So if this is 10 and that's 10, if I take 3 away from both, you get 7 equals 7.
Can you go up a little bit? If A, B, and C are collinear, so they're on a straight line, and B is between A and C, and if we know that BC equals 10, and AB equals 15, move this. We know that's 15. We know that's 10. Anybody want to take a shot that you know that AB plus BC is equal to AC? Say that? So we get to 25. So that's the segment addition postulate. Algebra would work too, as if you knew the whole distance of AC and you knew the distance of BC. If you want AB plus BC, if you wanted to subtract BC from the other side, that goes into the segment subtraction postulate, which works as well. The algebra will work easily and nicely. We good? Anything more on this page? Mm-hmm.
We're done. All right, let's cover up so next period gets the surprise. That's all the top.
Okay, if our, oh wait, we don't need that coordinate plane. I don't know why it's there. So I guess that's why it's crossed out. Okay, so if R, S, T are collinear, so if we had, so R, S, T are collinear, and S is between R and T, and if we knew that RT, so from here to here, is 20, and we knew that ST was 8, find RS. Logic talking to you that it should be 12. Why can I say it? What postulate? Segment subtraction postulate. So you're having to tell me why, not just assuming the algebra always takes place. You're using the numbers of math to do it. So a way to go through this problem would be like this. You go RS plus ST is equal to RT. And this is segment addition postulate. Do you agree? And then I could do RS plus 8 equals 20. What mathematical operation did I take place that you know but you don't want to say? It's an easy one. What? I heard it. Not subtraction. Substitution. Substitution. Okay? And then I guess you could say this. Why can you say that? What took place? Angle subtraction postulate. So you're given the reasons. There's definitely reasons that exist. If you don't give me the reasons, you're going to start missing points. And this is where you start getting kind of mad going, but it's obvious. That's not the reason. So it's like we're in a court now of math where you have to use all of the rules. They have to exist for a reason. Can I erase these? All right, let's see what we do here. Graph the points -2, -5. -2, -5. Call that x. And then -2, 3. Call that y. W is -4, 3. And z is 4, 3. Do everything right? -2, -5 is x. Gotcha. -2, 3 is y. -4, 3 is w. And 4, 3 is z. Find x, y. And so we're looking for the length of each of those. I'll have to continue these tomorrow. Cool? Sorry I ran out of time. I didn't want you to lose sleep. So if we ran out of time, we didn't have time to do stuff. That means I would say maybe take a look at the next assignment. Maybe start it if you can, but you don't need to be finished with it. Sound good?